This is the Math 3 Unit 3 review worksheet, preparing you for our test. So number 1 through 3 states, for each of the following functions, determine the end behavior. And so what we have to remember on 1 through 3 is the pattern of the end behavior. We look at two things. We look at the leading coefficient, and all we care about is whether it's positive or negative. And then we care about the degree of the polynomial. Remember, the degree is the highest power, and in case of degree, we care if it's odd degree or an even degree. And so we have 4 scenarios that we can run into if we end up with an odd. Well, so here's the thing. The leading coefficient, if the leading coefficient's positive, the right side will end pointing up. If the leading coefficient's negative, the right side will end pointing down. So this is the right side. Okay. Now if the degree is odd, then left and right sides will point in opposite directions. It doesn't matter what's in between, we're just looking at the end behavior. And if the degree is even, then both sides, left and right, will point in the same direction. So something went wrong here. We said odd is pointing in opposite directions, but I did not draw that. Sorry about that. There we go. And so let's take a look at number 1. Number 1, the leading coefficient is 5, which is positive. So we have a positive leading coefficient, and the highest power is 3, which is an odd degree. So positive leading coefficient, odd degree. So the end behavior is what I highlighted. We say left side is pointed down. Well, I'm just going to draw it in here. Okay. So left side pointed down, right side pointed up. And we have no idea what's happening in the middle yet. Number 2, the leading coefficient is -1, so negative leading coefficient, and the highest degree is 1. Remember, that's x to the power of 1, so it's an odd power. So negative leading coefficient, odd power. So I will highlight it in green. We're looking at the top right case. So the left side is pointing up, the right side is pointing down. And in the third case, we have an even degree and a positive leading coefficient. So positive leading coefficient, even degree. The leading coefficient is positive 4. The degree is also a positive 4. So both are even. I'll highlight our scenario here in blue. Both sides are pointed up. Left side's pointed up, right side's pointed up. They both go to infinity. Alright, number 4 says to define the following. A is a relative minimum. A relative minimum is a point where the graph changes from increasing to from decreasing to increasing, because we go down to the minimum and back up to the from there. Relative maximum is very similar. It's a point where it changes from increasing to decreasing. An x-intercept is where your graph crosses the x-axis. I'll say meets the x-axis because it doesn't necessarily have to cross it. So where the graph meets the x-axis. Y-intercept is where the graph meets the y-axis. Roots are solutions to an equation. Number 6, how many? I'm sorry. We are back here. So solutions to an equation, and the particular equation is f of x equals 0, or it could be g of x or whatever function, but they're values that you plug into an equation to get 0. They can be real numbers, they can be imaginary numbers, they're roots. Zeros are the same as roots. Solutions to f of x equals 0, same as, this is also known as roots or zeros. These are also known. The x-intercepts can also be seen as a root, a zero, a solution. Thing with x-intercepts is all x-intercepts are real numbers, whereas roots, zeros, solutions, they can be real or imaginary. Number 5, we're drawing 3 different possible sketches of this 4th degree polynomial. We're going to assume that a is not 0, because if a was 0, then it would no longer be a 4th degree polynomial. And so if a is positive, first of all, the highest degree is 4, it's even, so both ends, left and right end, are going to point in the same direction. So if a is positive, we have the left and the right end pointing up. And then what happens in the middle, we have a little bit of freedom to work with. So it could look like a parabola. Even though it's 4th degree, it's possible that it can look that way. It could also be pointed up. And look something like that. If a is negative, then both sides would be pointed down. And it looks something, we can do like an upside down parabola. Would work. Okay. So those are three possible sketches of this fourth degree polynomial. Number 6 is asking how many intercepts, x-intercepts, does each function have? Thing that's true about all x-intercepts have a y value equal to 0. So to solve for any x-intercept, you set y equal to 0. So in part A, we could say 0 is equal to 2x times x squared minus 1. And then we can set each factor equal to 0. So 2x equal to 0, x squared minus 1 is equal to 0, and then we can solve for x. If I divide by 2, I get x is 0. Here we can factor further the difference of two squares, so x plus 1 times x minus 1 equals 0. So if x plus 1 is 0, we get x equals negative 1. And if x minus 1 is 0, we get x equals positive 1. So we see there are three different x-intercepts for A. For part B, start the same way. I'm going to change the color here so it's easier to keep track. Set g of x, that's your y, equal to 0. So 0 equals 2 times x squared plus 1. The x squared plus 1 is a factor with a variable, so set that. Well, here if we divide both sides by 2, we get 0 is equal to x squared plus 1. And then subtract 1, and you get x squared equals negative 1. If you take the square root of both sides, you end up with the absolute value of x is equal to the square root of negative 1. But remember what the square root of negative 1 is I, the imaginary number. And so we can keep going here. If the absolute value of x is I, then x can be positive I, or x can be negative I. Both are not real, so B has no x-intercepts, because x-intercepts need to be real. And lastly, C, if we set our y value, which is h of x, equal to 0, then we can take each factor this is x plus 2 squared, so it's really x plus 2 times x plus 2. So we can take each factor and set it equal to 0. So 3x to the 4th is equal to 0. X squared plus 2 is equal to 0. And then we have two of these. I'm just going to write one of them. So x plus 2 is equal to 0. If you divide by 3, you get x to the 4th is equal to 0. The first one, you end up with x equals 0. The second one, you end up with x squared equals negative 2. When you take the square root of both sides, you end up with the absolute value of x equals the square root of a negative number. Not going to be real there, right? Whenever you take the square root of a negative number, it's not going to work out, so you end up with x equals positive and negative I root 2 there. And then third case, we end up with x equals negative 2. So keep in mind though, so far we've got two different x-intercepts, x equals 0 and x equals -2. But they have multiplicities greater than 1. The first one, x equals 0, has a multiplicity equal to 4 because we had x to the 4th power, right? X to the 4th power is x times x times x times x. So we really could have viewed this as 4 different factors, each one x, and set each x equal to 0. So we get x equals 0 4 times. And so multiplicity just is talking about repeating the same factor. So x equals 0 has a multiplicity of 4. X equals -2 also came from 2 different factors. So this gives us a multiplicity of 2. So how many x-intercepts are there? Well, if you are including multiplicity, you'd say 6. But if you're talking about different x-intercepts, there's only 2 distinct x-intercepts. So we'll say that. 2 distinct or different x-intercepts. Seven through 10, we're to write each function in completely factored form over the integers for part A. Part B, we're to find all the roots, real and imaginary, with their multiplicity if different from 1. And part C, we're here to state how many x-intercepts does the function have. So number 7, we have a 3rd degree polynomial, and we're going to work on factoring this. When you have 4 terms, we can try factoring by grouping. And so let's do that. So we look at the left half, the 4x to the 3rd and the 20x squared, and ask ourselves, well, what can we divide both 4 and 20 by? We can divide them both by 4. What can we divide x cubed and x squared by? X squared. And if you divide both of them by that, what do you end up with? Well, if I divide 4x cubed by 4x squared, you get x. If you divide 20x squared by 4x squared, you get 5. Then look at the right half. Both of those we can factor out or divide them both by -9, and we're left with another x plus 5. Now, if you view this polynomial as 2 terms separated by that minus sign before the 9, both those terms have a greatest common factor of x plus 5. So we factor that x plus 5 out. And we end up with 4x squared minus 9. Okay. If you're having trouble seeing what happened here, both terms had this x plus 5. So I'm dividing the left term and the right term by x plus 5. When I do, the left term is left with the 4x squared, the right term is left with the minus 9. Let's factor one more time. The 4x squared minus 9 is a difference of 2 perfect squares. 2x times 2x gives us 4x squared, and 3 times -3 gives us a -9. It's a shortcut that we can take only when there's a difference, when there's a minus sign between 2 perfect squares. Okay, so now we know this is completely factored because all our factors have a highest power of 1. And so we've done part A. Part B says find all the roots, real and imaginary, with their multiplicity. So To do that, we set f of x equal to 0 and solve. Here we set each factor equal to 0, so when x plus 5 is equal to 0, we get x is negative 5. When 2x plus 3 is 0, we get 2x is negative 3 divided by 2, x is negative 3 divided by 2. And when 2x minus 3 is 0, we get 2x is equal to 3, and divide by 2, x is equal to 3 over 2. So those are our three roots. All of them have a multiplicity of 1 because they're all different from each other. And so part A, I will highlight here. Part A is said to factor over the integers. Part B said to give all the roots, real and imaginary. That's part B. Sorry. And then part C, how many x-intercepts? So for part C, we're going to state 3 x-intercepts. Because really what C is asking is, you take a look at your answer to B and count how many of those are real, not imaginary. So that is part C. Okay, number 8. We're going to first start by trying to factor this. Notice both terms are divisible by 2 and x. So I'm going to factor out 2x. And I'm left with 64 x to the third plus 1. Notice we have a sum of two perfect cubes. 64 is 4 to the third power, and 1 is 1 to the third power. So we can factor, when you have a sum or a difference of two perfect cubes, that will be factorable. So y equals 2 times x, and then as we're factoring our sum of two perfect cubes, we're going to get a binomial and a trinomial. The binomial, you take the cube root of 64x cubed, which is 4x, plus, because it's a sum of two cubes, and then you take the cube root of 1, which is 1. So 4x plus 1. To create your trinomial, you take that 4x and square it. So 4x times 4x is 16x squared. If you used a plus sign between the 4x and the 1, which we did, the next sign is going to be negative. Those two signs will always be opposite of each other. Next term, you take the 4x and the 1 and multiply them together to get 4x. And then the last term is always positive and comes from 1 squared, or 1 times 1. And you can always check to make sure you're doing this right by multiplying everything out. You check 4x times 16x squared, 4x times negative 4x, 4x times 1, and then 1 times 16x squared, 1 times negative 4x, and 1 times 1. And simplify that, and it should all simplify to what you started with. We can try factoring further, but that 16x squared minus 4x plus 1 is not going to factor for us. One way to tell is it's a trinomial, and so we look for two numbers that multiply to 16 times 1, which is positive 16, and add to negative 4. You can try every possibility, it won't work. And so because that doesn't work, it doesn't factor. Okay, so we have done part A. Part A said to completely factor over the integers. Part B now is to solve and find all the roots, whether imaginary or real. So set y equal to 0. Set each factor equal to 0. And solve for each factor. So the first one you divide by 2 and you get x is 0. Second one you subtract 1, divide by 4, and you get x is negative 1 divided by 4, or negative 1/4. And then the third one, because it's quadratic, we're going to plug this into the quadratic formula. Remember, the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. In our case, a is 16, b is negative 4, and c is 1. So carefully plug all this in. We have a negative 4 plus or minus the square root of negative 4 squared minus 4 times 16 times 1. All of this is over 2 times 16. As you're plugging things in, notice wherever I had a variable, the a's, b's, and c's, I plug them in and put parentheses around them. This is important, especially when you have a double negative, to help you from making any little errors. Now you simplify this. Negative, double negative, that's going to give us a positive 4 plus or minus the square root. Negative 4 squared is positive 16 minus 4 times 16, so minus 64, all over 2 times 16, which is 32. Keep going. 4 plus or minus 16 minus 64 is going to be negative 48, so square root of negative 48 over 32. We need to simplify our square root if we can. There's a negative, so we're going to have the imaginary I out in front. But think about the square root of 48. 48 is 16 times 3. 16 is 4 times 4. And so we can, and if you want to keep going, you can. You can do, say, 4 is 2 times 2, and 4 is 2 times 2. So this is 4 plus or minus I square root of 2 to the 4th power times 3. And the square root of 2 to the 4th power is going to be 2 to the 2nd power. Don't forget all this is over 32. So now we have 4 plus or minus 2 squared I square root of 3 over 32. The 2 squared came from the square root of 2 to the 4th. You end up cutting your exponent in half. That's 4 plus or minus 4i root 3 over 32. And now divide the whole, everything on top and bottom by 4, and you end up with 1 plus or minus I root 3 over 8. Notice this is 2 roots split up in 1, right? So this is really 1 plus I root 3 over 8 and 1 minus I root 3 over 8. Just know there's 2 distinct roots, but we tend to just group them together. So what I highlighted here or outlined here is the way we're going to write it, but don't forget that plus or minus indicates there's two of them. So x equals 0, x equals negative 1/4, and x equals 1 plus or minus I root 3 over 8 give us all of our roots. So that's part B. And so there are 4 different roots. And so part C says, well, how many of those are real? How many are x-intercepts? So x equals 0 is an x-intercept, x equals negative 1/4 is an x-intercept, but the other 2 are not because they both have the imaginary I. So 2 x-intercepts. Number 9. We're factoring first. Here we have 4 terms. We can try factoring by grouping like we did in number 7. I'm going to save us the time though, because in this case it doesn't work. Factoring by grouping is just a tool that we can try to use, but sometimes these tools don't work, and so we can try, but it doesn't work. That's why they're giving us this second piece. They're telling us what one of the factors are. So if we know what one of the factors are, we can end up dividing our polynomial by x minus 7 to get the rest of the factorization. I'm going to use synthetic division to do this, and we can use that here. So to set up our synthetic division, we're going to put a 7 from the x minus 7. Using the opposite, we had x minus 7, here we're using a positive 7. And then a 1, which is the leading coefficient of x cubed. Leave a little space. Negative 12, which is the leading coefficient of x squared. 41, which is the leading coefficient of x. And negative 42, which is your constant. As you write this, make sure you're not skipping any powers, and we're not. We got cubed, squared, first power, and then no x. And the pattern to this is whatever that first number is, in this case a 1, bring it straight down. So we got a 1, and then multiply 7 times 1, which is 7, and add that product to the next number up at top. So 7 times 1 plus negative 12. Or you can say 7 times 1 minus 12. Well, 7 minus 12 is negative 5. Write that result here. And do this again. 7 times negative 5. And add 41 to that product. Well, 7 times negative 5 is negative 35. And negative 35 plus 41 is positive 6. And if we're working with a factor, your remainder should be 0. So this last one we should get 0 as an answer if we're doing this right. So 7 times 6 is 42, plus a negative 42 gives us a remainder of 0. That last one is always your remainder. So I usually put a little separator here to say, okay, that number, the remainder is a little different than the first 3. This process gives us our factorization. That 7 is representing our binomial factor, which is x minus 7. And then the 1, negative 5, 6 represents our trinomial factor, which is x squared, 1x squared, minus 5x plus 6. So now f of x has been factored a little bit. We may be able to factor more, and let's try. The x squared minus 5x plus 6, we're looking for 2 numbers that multiply to 1 times 6, which is 6, and add to negative 5. We should come up with negative 2 and negative 3. And if the leading coefficient is a 1, then we can take the shortcut and go to direct factorization. So we get f of x is x minus 7. And then the x squared minus 5x plus 6 factors to x minus 2 and x minus 3. Because we got the negative 2 and the negative 3. That's a shortcut. The longer way and the process that shows why this works would be splitting that negative 5x into negative 2x and negative 3x, and then to factor by grouping, and we'd end up with this result. It's a bit more work, so we're taking the shortcut here. So that's part A. We have fully factored over the integers f of x. Part B, we want our zeros, so we end up taking each factor, setting it equal to 0. And solving for x. So we get x is 7, x is 2, and x is 3. That's part B. And then ask for how many x-intercepts there are. So you look at all your roots and ask, well, how many roots do I have, and how many of those in particular are real? And all of them are real in this case, so we have 3 x-intercepts. Okay, last one, number 10 of this type. Number 10, here we have, it's a 4th degree polynomial, but it's written in somewhat of a quadratic form. Because, well, if you have 3 terms, and one of them is a constant, the highest power in this case is 4. If the term in the middle has, the power here is half the highest power, it meets somewhat of a quadratic form, and you can attempt to factor it. And so that's what we're going to do here. We're going to attempt to factor it as we would a quadratic, even though it's not a quadratic. So I'm looking for 2 numbers that multiply to negative 36 and add to 9. So in this case, 12 and negative 3 would work, because 12 times negative 3 is negative 36, and 12 plus negative 3 is 9. So then we split this up. F of x equals x to the 4th. We're splitting up the 9x squared to 12x squared minus 3x squared minus 36. Now when you split this up, make sure the 12 and the negative 3 are the same term as the middle term. So it's coming from the 9x squared. Because it's a 9x squared, both of these have the x squared. They need to be like terms. Then we continue with factoring. We're going to factor by grouping. The left half, the x to the 4th and the 12x squared have x squared in common. So factor out x squared, and we're left with x squared plus 12. The right side, the negative 3x squared and the minus 36 are both divisible by negative 3. And when you factor that out, we end up with x squared plus 12. Continue factoring, we can factor out the x squared plus 12 in both terms. That's the GCF. And we're left with x squared minus 3. So this is as factored as we can do over the integers. If you try to factor any further, it won't work. We know that if you have a sum of two terms, they don't have a GCF that we can factor out other than 1. There's just nothing we can do, no factoring methods we've looked at that will help us here. So part A is done here. Asks us to factor over the integers completely. Part B, we need to find our zeros. So we set each factor equal to 0. X squared plus 12 equals 0. And x squared minus 3 equals 0. And solve. So on the first one, I subtract 12. And then take the square root. So x is the square root. When I take the square root of x squared, that's the absolute value of x. And the square root of negative 12. Remember the square root of a negative, that's when you get the imaginary number. And 12 is 3 times 2 times 2. You got a pair of 2's, so we can have 2 square root 3. That I comes from the negative, so absolute value of x equals 2i square root 3. And then we can split this into x equals positive 2i root 3 and x equals negative 2i root 3. The second equation, the x squared minus 3 equals 0. We're going to add 3. We get x squared equals 3. Take the square root of both sides. We get the absolute value of x is equal to the square root of 3. And so because the absolute value is equal to the square root of 3, we get x is equal to the square root of 3. And x is equal to the negative square root of 3. And so we end up with 4 zeros. 2 of them are imaginary, 2 are real. None of them are rational. So that's part B. And then part C asks us how many x-intercepts this function has. And so for part C, we're going to say 2 x-intercepts. Because x-intercepts are the real zeros, or the real roots of your function. And the square root of 3 and the negative square root of 3 are your 2 real x-intercepts. All right, on to 11. 11 says to sketch the graph for each of the following. Label the x and y intercepts. Hint, finish factoring each first. Okay, so on 11, we're going to finish factoring. Notice the x cubed minus x squared minus 2x, we can factor it in an x. So we get, we already had an x out in front, so x times x, and then in parentheses we get x squared minus x minus 2. So y equals x squared, that's your x times x. And then the x squared minus x minus 2 we can factor further. We're looking for two numbers that multiply to negative 2 and add to negative 1. And negative 2 and positive 1 would work out for us in this case. Because the leading coefficient is 1, we can take a shortcut and just write our answer directly, x minus 2 times x plus 1. So now it's completely factored. And So in sketching our graph, there's a few things that we need to pay attention to. First of all, what's the degree of this function? So our degree is equal to 4. X squared carries a degree 2. The x minus 2 carries a degree of 1. And the x plus 1 carries a degree of 1. So you add the degrees of their factors up, 2 plus 1 plus 1, to get the degree of your total polynomial. The reason this is degree 4 is if we multiplied everything out, we would start with an x to the 4th, and that's where we get our degree from. The leading coefficient in this case is positive 1. So we have an even degree and a positive leading coefficient. So this tells us about our end behavior. Because the leading coefficient is positive, the right side of our graph is going to point up. And because the degree is even, the left side is going to point in the same direction. So both sides are pointing up. Since we have it in factored form, it's easy to find our x-intercepts. We can set our factors equal to 0. And solve. So first one we get x is 0, but notice the multiplicity is 2, or even, so it's going to bounce at that point. Next one we get x is 2 with a multiplicity of 1, and then we get x equals negative 1 with a multiplicity of 1. And then so we have our x-intercepts ready to go. We have our end behavior ready to go. We just need now our y-intercepts. So for 11, to find a y-intercept, you plug in 0 for x. And if we plug in 0 for x, we're going to get 0 because we end up with y equals 0 squared times 0 minus 2 times 0 plus 1. Well, that 0 squared is 0, and then you're going to multiply that 0 times the parentheses, whatever we get, negative 2 and 1. We just end up with 0. So 0 is our y-intercept. We're going to put all this information together to get a graph. And I know I'm moving over to where number 12 is, but our graph, I'll put our graph here, and then I will move it over to where 11 is, okay? So mark out first when you're graphing where your x-intercepts are at. So at 2, at negative 1, and at 0. 0 is also our 0, 0 is going to be our y-intercept as well. And so the right side is pointing up, so is the left side. And then I'm going to start from the left side and move towards the first x-intercept, which is negative 1. And then note the multiplicity of negative 1 is 1, so it's an odd, so I pass through. Then I'm going to come back up to the next x-intercept at 0, which has a multiplicity of 2, so it's got to bounce back from the x-intercept, come back down, and then come back up to the next x-intercept, which is 2, and we're going to pass through because it's an odd multiplicity. And so the end behavior we see is pointing up. We see it's hitting our x and y-intercepts the way we want, and that's our answer. So I am going to take this work now and move it over. To make room for number 12. All right, number 12. We're working through it the same way. Factor further. So we're looking for two numbers that multiply to negative 4 and add to negative 3. negative 4 and 1, so x minus 4 times x plus 1, and we already had another x minus 4. So we got three factors. The x minus 4 gives us a 0 at x equals 4. The x plus 1 gives us a 0 at x equals negative 1. And we got another x minus 4, so that gives us a multiplicity of 2 for x equals 4. For n behavior, we need to know the degree. The degree of this function is 3 because we have well, we got three linear terms, each of degree 1. 1 plus 1 plus 1 is 3 if we look at the factored form. The leading coefficient is positive 1, and so we have an odd degree positive leading coefficient, so the right side points up, the left side of the graph, the end behavior, points down. Lastly, we're looking for our y-intercept. For our y-intercept, we plug in 0 for x, so 0 minus 4 times 0 plus 1 times 0 minus 4, and we end up with negative 4 times 1 times negative 4, which is 16. So we have a y-intercept at 16. So we're going to put all this information together to create our graph. I'm going to scoot this over to the right. And sketch our graph here on the left-hand side. I'm going to first mark out my x and y intercepts. So x-intercept over here at 4 and at negative 1. And then my y-intercept is up here at 16. My left end is pointed down to negative infinity. So I'm going to start there, move up to the negative 1, decide am I going to pass through. Well, at negative 1, multiplicity of 1, so I'm going to pass through all the way to 16. It probably shouldn't be curved like that, but I reach up to 16 and come back down to 4. And when I come down to 4, I'm going to bounce back up because I have a double multiplicity there. And end pointed up, which is what we want because we want our right end behavior pointed up. And there's a sketch of number 12. Number 13. We're going to finish factoring this, so we get negative 1/2. When we factor the first part, we're looking for two numbers that multiply to negative 3 and add to 2. X plus 3 times x minus 1. And the second one, two numbers that multiply to negative 18 and add to negative 3. X minus 6 and x plus 3. Yeah. So here we have four factors, four linear factors that give us zeros at x equals 3, 1, and 6. And the 3 is a double multiplicity, so it's going to bounce at 3. We're going to use that for our graph. Also, we want to know our degree of this function. It's going to be a degree 4 because we have 4 linear factors, or 4 factors with degree 1. And then our leading coefficient is negative 1/2. So negative leading coefficient tells us the right side's pointed down. Even degree tells us the left side's pointing down in the same direction. So we're going to use that. And then lastly, we want our y-intercept. The y-intercept comes from plugging in 0 into this equation, wherever there's an x. So we end up with negative 1/2 times 3 times negative 1 times negative 6 times positive 3. And so we got 3 negatives, so it's going to end up being a negative answer. 3 times 3 is 9, and 6 divided by 2 is 3. 9 times 3 is 27, so negative 27 is our y-intercept. So that's what you should get when you multiply all that together. So let's finish with a graph. Y-intercept down at negative 27. X-intercepts at 1. Should be negative 3. And positive 6. Start with the left end pointed down. Move towards your first x-intercept, which is at negative 3. Going to bounce off negative 3 because it's a double multiplicity. Come down to negative 27. Go back to 1. Going to pass through 1 because it's a multiplicity of 1. Come back to 6. Go through 6 because it's a multiplicity of 1. And there's our sketch. We're going to write an equation. It's an equation, so there's multiple possibilities. There are other equations that may, there's more than one possible answer here. But what is true is our x-intercepts. We got one at x equals negative 3, x equals 0, and x equals 4. So we turn our x-intercepts into factors. X plus 3, x, and x minus 4. So our function, put our factors side by side. Usually you start with the x in front, times x plus 3, times x minus 4. And then check the end behavior. Right side's pointed up, left side's pointed down. So we need an odd degree. And because the right side's pointed up, we need a positive leading coefficient. And we have that. So this works. I could also put the number 2 in front of the x, it would still work. So there's more than one possibility here. Number 15 says write the equation, so meaning there is only one correct answer here. Well, we have an x-intercept at negative 1, an x-intercept at 1, and an x-intercept at 2. But notice at the 1 it bounces, so we need an even multiplicity. So factors, changing these to factors, we have x plus 1, we have x minus 1, but I'm going to make it squared to get multiplicity of 2, and we have an x minus 2. Call this g of x. Lastly, we're not sure. We know this thing goes through the y-intercept at 3, so there's some leading coefficient a. We know that a has got to be negative because the right side's pointed down, but we're not exactly sure what number is going to make it 3 yet. So we're going to plug in that point, 0 for x, 3 for y. And we get 3 is equal to a times 0 plus 1, which is 1, 0 minus 1 squared, so it's negative 1 squared, and 0 minus 2, which is negative 2. So 3 equals a times 1 times 1 times negative 2, which which is just -2. Divide by -2, and you get 3 over -2 is equal to a. So now we can plug that back in for a and write g of x is -3 over 2 times x plus 1 times x minus 1 squared times x minus 2. We're going to write a 6-degree polynomial with roots 0, multiplicity of 3. Okay, so well, if the root is 0, our factor is x. If the multiplicity is 3, we're going to make that x cubed. We want our root to be 5 over 2. Well, if our root x equals 5 over 2, multiply both sides by 2, and you get 2x equals 5. Subtract 5, you get 2x minus 5 equals 0. So our factor is going to be 2x minus 5, which has, and 3, so our factor is going to be x minus 3 with a multiplicity of 2. And this function goes through the point 136. So let's put together what we know so far. F of x is equal to some leading coefficient, don't know that part, times x cubed times 2x minus 5 times x minus 3 squared. And if I plug a 36 in for y, I get 36 when I plug in a 1 for x. That's a times 1 to the third power times 2 times 1 minus 5, so that's 2 minus 5, times 1 minus 3, so it's squared. So 36 equals a times 1 cubed is 1, times -3 times -2 squared, which is 4. Divide both sides by -12, and you end up with -3 is equal to a. Plug that back in, and we have our function f of x equals -3x cubed times 2x minus 5 times x minus 3 squared. 6th degree. It's a polynomial with those given roots and those multiplicities, and it goes through the point 136. 17. We want a cubic polynomial with zeros -2, 2, and 1. So if those are the zeros, our factors will be x plus 2, x minus 2, and x minus 1. So let's call this g of x equals, and we're not sure what the leading coefficient is, but it's got a y-intercept of -3. That means it goes through the point 0, -3. So if I plug in 0 for x, I get -3 for y. So I plugged in 0 for x, that gave me 2 times -2 times -1, which is 4. So -3 equals 4 times a. Divide by 4, -3 over 4 is a. Plug that back in, and you have your function g of x is -3/4 times x plus 2 times x minus 2 times x minus 1. We're given a function here. It says, given this function with 5 key labeled points, sketch each transformation and label the 5 key points. Okay, so we need to first identify the transformation and then sketch it. 18, that f of x plus 5 tells us we're moving everything to the left 5 units. So if we take each of these points and move them 5 to the left, where will we end up? Well, this first one at 0, 0 is going to be over here at negative 5, 0, right? The 1, negative 4, if we move that left 5 units, it's harder to see without a grid here. But what's happening is you're taking the x value in that coordinate and you're subtracting 5 from it. So if we take 1 minus 5, we get negative 4. So that's going to be moved over. The x value becomes negative 4. The y value does not change. It stays the same height because we're just moving things to the left. So we've taken care of the first point, the second point. We're on to the third point. Take the x value 2 and subtract 5 from it, and you get negative 3. So that's over here at negative 3, comma 0, same height. Done with that one. We have the one above at 4, 8. Subtract 5 from the x value 4, and you get same height right here at negative 1, 8. And then one more point, 5, 0, subtract, and you end up at 0, 0. And if I were to sketch that, something like that. And I can grab that. Move it if we need. But there it is. And that's the kind of the process we would use to get that. Here's our x-axis. Our y-axis is here. Okay. Okay, number 19. 19, we have f of x plus 4. So what that's going to do is move everything up 4 units. Okay, so let's look at the original graph. And if we take each point and move it up 4 units, what's happening here? So originally it was 0, 0, so now it's up at 0, 4, right? Here we were at 1, negative 4. If we move up 4 units, we're adding 4 to the y value. So our y value was negative 4, so negative 4 plus 4 moves us up right here at 1, 0. Now take the 2, 0. If we move that up 4 units, we're adding 4 to the y value of 0, so we're adding 4 to the height. Still the same x value, so we're at 2, 4. The 4, 8, when you move that up 4, we're now at 4, 12. And then the 5, 0, when you move that up 4, we're at 5, 4. So all the x values stayed the same. The y values changed. So I could take those points and transfer them. I'll move them next to my problem here. Those are the key points we wanted. And I'll sketch my graph through them. Here's your x-axis. Here's your y-axis. Okay. And then the last one, 20, negative f of x minus 4. So what's happening here? So we have a negative in front of the f of x. That is a reflection about the x-axis. Okay, that's what's going to happen first. And then the minus 4 is going to move us down 4. So first reflect about the x-axis, then move everything down 4. So let's go back. Remember that we're going to reflect about the x-axis first, then move down 4. Well, if you have a point on the x-axis, so let's start with 0, 0. When you reflect that about the x-axis, it's still on the x-axis. And then you're going to move it down 4 units, so we're subtracting 4 from the y value. And it's going to be right here at 0, negative 4. Next point, 1, negative 4, when you reflect it, it's going to go up here above the x-axis at, so initially that's at 1, 4, that's after the reflection. And then I'm going to go up 4 more, so I'm going to be at a height at, I'm sorry, I'm not going up 4, I'm going down 4, aren't I? So because we're reflecting and then dropping down 4. So when I take that point and drop it down 4, now we're on the x-axis at 1, 0. So I'm going to erase the stuff I was using to help me get there, because I'm already there now, and put in that point 1, 0. The point 2, 0, if you reflect it first about the x-axis, it's still on the x-axis, and then you transfer it down 4 units. So we're at 2, negative 4. The point 4, 8, when you take that and reflect it around the x-axis, initially it's going to be pretty low at 4, negative 8. And then we want to drop down 4 more, so it's going to be at 4, negative 12. And last one, the 5, 0, when you reflect that across the x-axis, it's still put there, and then you drop it down 4 units to 5, negative 4. So those are our key points. And when we sketch our graph through this, it's going to be the reflection, so it's going to be this picture turned upside down. Let me grab the points. Transfer them down. Okay. And so what's going to happen is it's going to start this direction, raise up, come back down, come back up. And we have our x-axis here, our y-axis here. Something like that. A little bit of a messy sketch, but you got your points and you have somewhat of a sketch there.